Okay, well, yeah, this is going to be a little bit different because I'm going to give a zoologist's perspective to what we can know about life, what we can know about extraterrestrial life and alien life. And, you know, you might ask why you want to hear from a zoologist. And the obvious sort of question you might ask, well, we haven't actually discovered any alien life. So what has the zoologist got to say about it? Astrobiology and everything that you've heard so far has been a lot about biochemistry, a lot about metabolism, and that's the way it should be, because we don't understand the nature of all the different kinds of life that could exist. But at some point, we're going to have to start thinking about complex alien life, more than just microbes, something that's more similar to the kinds of environments that we see on Earth. And when we want to do that, that means we need to understand how ecosystems evolve. Because complex life, animals, trees, mushrooms, can only come about through complex interactions. It's the only way that complexity itself is favored in evolution is if there are a lot of complex interactions. And fortunately, we have lots of complex interactions here on Earth. And we actually understand quite a lot about how complex interactions work and how they generate the kinds of evolutionary outcomes that we see. So my claim is that there are some universal laws of biology. They're not like laws of physics in that the predictions that we can make from the universal laws of biology are different in nature from the predictions we make from physics. Ball rolls down a hill on Earth, it rolls down a hill on another planet as well. Laws of biology don't give us that kind of precision, but they exist and they are universal. So when I talk about universal laws of biology, we need to make a little bit of a distinction between what I would call mechanisms, and most of us will be familiar with all kinds of metabolic mechanisms that are clearly essential for life on Earth, and they may be similar to the mechanisms that exist on other planets as well, or they may not. There may be other mechanisms that are taking place that are driving the metabolism that, as we just heard, life is a chemical reaction. It needs some sort of metabolism to capture and mobilize energy. But the details of how that might happen could conceivably vary. On the other hand, there are processes that are quite universal. We know, for instance, that natural selection is the only way that complexity can really accumulate. There are laws of game theory, which are absolutely fundamental to how we understand the nature of life on Earth today. And we know that those are purely mathematical laws that will apply anywhere where natural selection is operating. There are laws of physics that come into it as well. And there's also the question of the dynamics of an ecosystem, the ways that different kinds of species interact with each other that generate the kind of complexity that we're talking about. So we all know there's an awful lot of planets in the galaxy. There's an awful lot of Earth-like planets in the galaxy, possibly 40 billion. We don't know what the probability of life arising is, so we can't say how much life there is in our galaxy. But we like to think there's quite a lot. However, if we look at the history of life on Earth, what we see is that for a vast amount of time, life was really simple. Okay, life arose on Earth really very quickly, very soon after liquid water formed on the surface. But complex life, complex animals, for instance, in the way you see in the upper picture, the sort of things that we might look at and say, oh yeah, those are animals like we understand them. They're very recent, right? Only really in the last 500 million years or so. So for most of the history of Earth, life was incredibly simple. Complexity accumulated very, very slowly at first. And that's a key feature of the way that life evolved on Earth. Now, it's true that Earth's quite relatively young relative to other planets. It could be that things are different in other parts of the galaxy. But if you were just to choose planets with a history like Earth at random, chances are you'd find some bacterial slime and not much else. also, during those 2 billion years, 2 billion years since from the origin of life until what we would consider modern complex life, there's some very strange things happened on Earth. So at least twice, the entire planet froze over from pole to pole. There's all kinds of weird random events, cosmic events, events caused by the interaction of the developing life on Earth and the physical system. And given that it was such a long time and so many coincidences happened, one might argue, as some do, that we can't really make predictions about what would happen on other planets that have sat through 2 billion years of simple life before complex life evolves. But I don't think that's true. And that's because essentially life is constrained. There are a lot of constraints that operate on life. Whatever you hear in science fiction, all these weird things that can happen, right? There are actually a lot of genuine constraints. There are physical constraints, there are constraints of evolution, and there are constraints of ecology. The way that life is constrained by the laws of physics is often quite straightforward, but we tend to forget them, like the laws of mechanics, right? If you want to move on a solid surface, you need to exert force on the surface. You don't want to be constrained by friction, so you have legs, right? You are in contact with the surface on only a very small area. Legs are incredibly useful, right? They've evolved over and over again on Earth because they are so useful, just like they're useful to organisms on another planet. The other thing that motion has shown us from life on Earth is that if you know where you're going, then you have a front and a back. And if you have a front and a back, then you have a left and a right. And the vast majority of animals on Earth are bilaterally symmetrical. Now, that could be a coincidence. It could be just a coincidence of life on Earth, but it doesn't seem to be. Bilateral symmetry seems to be so incredibly useful. It's hard to imagine how it wouldn't evolve on another planet. And if it did evolve on another planet, then those bilaterally symmetrical creatures like this flatworm you see here, which is thought to be sort of like superficially at least similar to some early animal life forms on Earth, they would have a huge advantage over organisms that were trying to move in a different way. It'd be much faster, much more efficient. So it seems likely that symmetry, bilateral symmetry, is something that's going to evolve over and over again. Now, of course, not all animals on Earth are bilaterally symmetrical. The vast majority, but there are still corals and there are still jellyfish that are not bilaterally symmetrical. And this tells us two very interesting things. Firstly, it tells us that diversity is going to arise, right? You're going to get organisms that exploit whatever niche is available. It's useful for the corals in their adult phase to be static, so they have this sedentary, non-moving lifestyle. It doesn't help them to be bilaterally symmetrical, and they do well out of that. In general, all opportunities that can be exploited by life will be exploited, given enough time. So just remember that where there are opportunities, we can expect life to exploit those opportunities. But the corals and the jellyfish are absolutely dwarfed by symmetrical animal life. They're a tiny, tiny, tiny minority simply because they're so easily outcompeted by the movement of symmetrical creatures. And this leads to a really important point that I think a lot of people talking about extraterrestrial life maybe forget, and an element of modesty is needed here, that weird and wonderful things will happen, right? Any predictions that we make, we can be sure that the exceptions to those will occur somewhere in the galaxy, but they will be rare. The obvious things will be common. The obvious mechanisms, the obvious solutions should be much more common than the weird and wonderful, which doesn't mean the weird and wonderful won't exist, but they're just going to be a lot rarer. So simple laws of physics, simple laws of mechanics give us some constraints that allow us to make predictions about some kinds of organisms on other planets. But there are other constraints that are not strictly due to the laws of physics. There are some constraints that are ecological. So I don't know if you've ever asked yourselves why we don't have flying whales on Earth. It's certainly not physically impossible. It's actually quite easy. There are plenty of, well, as we know, plenty of chemical processes and biological processes that produce hydrogen gas. You have a little pouch on your back and some bacteria. The pouch inflates with hydrogen and up you go. It's not physically impossible. We build these things ourselves. Why aren't there flying whales on Earth? The reason there aren't flying whales on Earth is because there's not much food in the atmosphere. Rarefied gas atmosphere, so solid objects tend to fall out of the atmosphere. There's just not much up there. And that's an important point, because while it'd be tremendously useful for a whale to be able to fly from one ocean to another and so on, they can't evolve that. They will not evolve that because they gain no advantage from going up in the air. And they gain no advantage because of the ecological constraint, because there's no food up there. Another kind of constraint which we can assume will be universal are the mathematical constraints of game theory. Game theory has played a very important role in understanding how evolution takes place on Earth. For those of you who are not familiar, I've got a little example here of one of the best sort of toy examples of game theory. It's called the hawk-dove game. So if you imagine yourself living in a society of doves, they're all very friendly, we all love each other, there's lots of food, we share our food, lots of free love, lots of mating, and no one fights with anyone else. It's a great place to live. And then along comes one hawk. Now the hawk, of course, can exploit the doves won't fight back. Very soon what you find, the hawks are incredibly successful and they take over and they take over the population from the doves. But the thing is that a population of hawks isn't a very nice place to be. You're always fighting, risk of injury, just wasting a lot of energy on competing. And so it's possible that here and there a few doves might be able to eke out an existence because they're saving their energy, that they're not going in for all this fighting. And we get what's called an evolutionarily stable strategy. Now, there are some lessons from this. One lesson is that optimality isn't always stable. So we'd all like to live in the society of doves, but we can't. It's just not stable. But more importantly, it makes a difference from an evolutionary perspective what everyone else is doing. What's best for you to do depends on what others do. And as we saw with the corals and the jellyfish, it sometimes pays to be different. There's a niche to be exploited by being different. So this idea that what's going to evolve depends on interactions is also very key to how we understand how complex life arises. Now, when you think about science fiction representations of alien ecosystems, so this is James Cameron's Avatar, you know, they kind of look a bit like Earth, right? You could imagine these being alien dragonflies and monkeys and so on. And the question is, are they subconsciously copies of life that we know from Earth? Or are the creators making an ecosystem that is in some way realistic? That is something that we could expect, the dinosaurs that eating nectar and so on. So let's think a little bit about ecosystems. Here's a sort of diagram you're probably familiar with from school. And the key thing about a food web like this is that the animals didn't just drop into place, into their respective places on this food web, right? The bald eagle doesn't just sort of go there because there are arrows waiting for it. The web and the animals evolved together. The interactions between the species and the species themselves can't be separated. Without the complexity of this web, there'd be no diversity of animals, and vice versa. They go 100% go together with each other. So I'm going to illustrate that with a little bit of a story from the history of life on Earth. So about 600 million years ago, we think that life in the oceans looked something a little bit like this. There were things that were like plants that were getting energy from photosynthesis. There were things that were getting energy from dead organic matter, some things that were grazing on the plants. Some of these creatures were animals. Some of them were things that weren't animals or plants or anything that we have today. But anyway, it was quite a relaxed sort of environment. There was a bit of grazing going on, but basically none of these animals were eating any other animals. We could see that because none of them had shells or teeth or anything like that. And then about 540 million years ago, something radical happened. All of a sudden, very, very quickly, within a few millions of years, really, the situation changed entirely. We see animals with legs, with spines, with shells. We see animals with eyes running away from things that want to eat them, or eyes to find the prey to catch. We see animals hiding and burrowing. The entire situation changed rapidly. The lack of predation that existed previously was unstable. It's like the population of doves. The moment someone starts taking a bite out of someone else, you have to defend yourself. You have to find a way, otherwise your offspring won't survive. And the key thing here is there's no going back. This is a ratchet. Okay, if a world without predation is unstable, the moment predation arises, it will be there from then on. We may find planets in the galaxy without predation, but they won't remain like that forever. The longer they exist, the more likely it is that predation is going to arise. And it was precisely with that Cambrian explosion, as it was called, with the sudden diversification of organisms into the modern forms that we recognize now, that was driven by the presence of predation. That's why animals had legs. They had to run quickly to catch their food or to get away from predators and so on. So going back to our food web, we could see that the primary producers as old as life itself, and certainly there were organisms that were feeding on them, alive or dead, and then inevitably along came the predators, and when the predators arrived, that meant a massive increase in animal diversity. Now, when you have predation, the next thing that you have is an arms race, right? You don't want to be eaten, so you protect yourself perhaps with some kind of armored skin, and then the predators have to get larger teeth to bite through the armored skin, then you want to get bigger armor and longer horns and so on. It goes on and on and on. Arms races are an inevitable consequence of predation. This is not something that's special about Earth. This is something that we can expect to see on any planet where predation has evolved. So those predators and the organisms that have found ways to avoid being eaten also fit into this complex interaction, the complex interactions between different species with different roles in the ecosystem. And it's that complexity that drives even more complexity, right? The more complex the ecosystem is, the more opportunities there are, the more possibilities for evolving new complexity. We can see this quite interesting graph of estimate of the diversity of life on Earth over geological time. So since the Cambrian explosion 540 million years ago, you can see that for a long time, diversity of life on Earth was fairly constant until the end of the Permian, and then there was a huge mass extinction. 90% of life on Earth went extinct, but since then diversity has been increasing and increasing steadily, even with a few blips, right? When 66 million years ago, when the meteor hit the Earth and dinosaurs went extinct, there was a blip, but diversity is continuing to increase. Once you reach a critical level of diversity, the opportunities available, and in the case of planet Earth, this was largely because of flowering plants, but when you get a certain level of complexity in the ecosystem, then diversity just grows and grows and grows, because there are so many opportunities and so many niches to exploit. Now, diversity does mean reproduction, okay? Reproduction is actually the only way the complexity can accumulate, because it's one of the requirements of natural selection, and we don't think complexity can accumulate without natural selection. If you're an immortal life form, you can't actually improve. And this is excellently demonstrated in Richard Dawkins' books. But then the question is, reproduction may be essential, but what about sex? If you look at asexually reproducing organisms on Earth, they're relatively simple. Certainly simple compared to sexually reproducing organisms, which is all the plants and animals and fungi that we know. Now, there's a lot of contentious discussion about why this is and how essential sex is for evolutionary complexity. But we do know there are reasons why true asexual reproduction is very problematic. Even bacteria, even those bacteria on the left that seem so simple, they have this sort of horizontal gene transfer, which is a way of shuffling heritable information that seems to be essential for avoiding some sort of evolutionary dead ends. So we don't know whether complex life on other planets must have sex in the sense that we know it. They may not even use DNA, so they may not have two parents, for instance. But some form of shuffling of heritable information seems to be likely or necessary if complexity is going to evolve, and that has some interesting consequences too. Arms races, like I said, are inevitable, but they're terribly wasteful. They're really, who wants to be a triceratops with this great big horns and shield and so on? What else can you do to avoid predation? Well, the solution that has come up again and again and again on Earth to avoid predation is to live in social groups. Social groups help protect you against predators. They can help you find food better. They help to defend against competing animals in the same species. Maybe you can build things. And social groups allow you to raise young cooperatively. Now, I haven't talked about what we call inclusive fitness, but it is a feature of evolution that if you have if you have reproduction in which there's a certain amount of relatedness between the parents and the offspring, then you get a tendency to evolve family groups and social groups, because it's to your advantage to make sure that your offspring survive and reproduce themselves. But living in groups is incredibly difficult. You may be defended from predators, but you're competing with other animals of your own species. And we all know that living in a society is complex. Eventually, the more complex the society, the more intelligence needs to evolve to deal with those complex social relationships within a group. So this is an example of a very macro process, okay? We know that all life needs energy. That's the nature of life. And therefore, there's competition for energy. Sooner or later, someone's going to take a bite out of you, steal your energy from you. So a lack of predation is unstable. If you've got predation, you've got arms races, that's very costly. Sometimes you can do a lot better, not by having huge horns, but by living in a large herd. But if you're living in a large herd, that's a complicated life. You need some sort of communication, you need some sort of intelligence to mediate the interactions in that group. So to summarize this all up, the lessons that I'm suggesting that we learn from looking at life on Earth, well, we know that life needs energy. Obviously, if you're living in an underground ocean, like on Enceladus, then you may not be photosynthesizing, but some form of energy capture is necessary so that you can mobilize that energy and drive your metabolism. If energy is important to you, which it is, then eventually predation will arise. Predation in terms of stealing energy from other organisms. If there is predation, then you better be able to run away. And if you want to run away, symmetry and legs are likely to arise as well. We think that sex is probably in some form of sexual reproduction or of shuffling of heritable information is probably necessary for complexity. And if there's sex, then there are families, and there are family groups. Together with the defense against predation, family groups means communication, it means intelligence, and maybe it means something a little bit like life on Earth. So my sort of take-home message is that by looking at the kinds of evolutionary interactions that we see on Earth, we can say a lot about the processes that we expect to take when complex life evolves on other planets, not just simple life, but complex life itself. So that's a very brief summary, and it's all there in my book if you want, in much more detail. And yeah, I hope there's some questions.
Indeed, yes. Thank you so much, Arik. Arik, a question here from Louis. How can we assume these laws of physics and ecosystems are likely the same and universal? Look at Earth versus Venus. Very different ecosystem allows us to imagine very different life. Look at Earth versus Europa. Very different ecosystems and physical properties allow the same. Might that not lead us to conclude there is no complete, not sure, a typo here, nothing possible there. But sure. You get the gist of what he's asking.
I get the gist, sure.
Yes.
So, okay, well, let's take those two in turn. So Venus is a great example, okay, because we had the recent speculation about possible life forms in the atmosphere of Venus. I don't know how they could have evolved. Let's say they migrated from the surface. But one of the interesting things, if you read the sort of Baines et al. Paper about proposed life cycles of these organisms through repeated cycles of condensation and evaporation of sulfuric acid. Yeah, that's a fantastic mechanism. But we have to ask ourselves, could that life achieve the kind of complexity that's postulated, assuming they are at least somewhat complex, without any interaction with each other? In other words, we can't just think about what organisms could exist in the atmosphere of Venus. We have to think how they would evolve. Is there any coalescence of droplets of sulfuric acid that would allow two of those individuals, microbial individuals, to interact and possibly to share heritable information? Because without that sharing of heritable information, it seems very unlikely, and there are mathematical reasons to think that it's unlikely that complexity could accumulate. So no one's saying that the same processes exactly will take place, but the principles on which we base our ideas and our understanding of life on Earth, they still apply there, right? You're not going to get complex diversity if there's not a diversity of niches, for instance. And if you need to exchange heritable information, then you need contact between those organisms. As far as Europa and Enceladus go, I mean, that's a really interesting example, because if life exists, let's say, on the underside of the ice surface of those planets, then you just have to think about the ecology. Yeah, it's different, but an organism, when it dies, will sink, presumably. And if you sort of turn that upside down and you imagine organisms living on the seafloor on Earth, it'd be like all of the detritus would be floating up into the air, and that's problematic, right? That's problematic, since a lot of the early organisms on Earth probably fed on detritus and dead organic matter. So of course things are going to be different, but it doesn't alter the fact that those interactions are what's driving the complexity, and these organisms will have to find a way to deal with the dead bodies that rise up into the sky.
Interesting. Arik, a question for myself. You were saying that the more diverse and the more complex ecosystems become, the more likely they are to beget greater complexity. So does complexity beget greater complexity?
That's right. Yeah. Well, and that's because, and that's largely because what is biological complexity? Biological complexity is exploitation of multiple niches, and there's no reason for there to be 10 different species of dragonfly unless they are exploiting different niches. They are using different phenotypic traits to achieve their goal in a better way. So what drives complexity is the availability of niches. Most niches involve interaction with other organisms, either with food organisms or predators, or just competitors, or even plants, for instance, that have to grow upwards to get enough light and not be shaded out by their competitors. That's still in an interaction between between species. And it's precisely the nature of those interactions that's driving the need for phenotypic innovation. So we need to grow faster, for instance, to get up above the other plants. So the more different kinds of species there are, the more opportunities there are for new niches.
Okay. One last question very quickly from Barbara to follow on from that physical processes question. We know other planets have very different gravitational properties, magnetic fields, pressures, radiation fields, etc. Which of these differential properties might change potential universal properties of life you've discussed?
Well, I think there'll be different constraints, of course. Obviously, if gravity is much less, then you may find that flying becomes easier, I suppose. But this is just variation. This is just variation on a theme. The principles are still the principles still apply. And I do think that, and here I may be wrong, and here I'm sure many other experts know much more about it than I do. But with the 40 billion Earth-like planets in the galaxy, I'm sure there is. I suspect there may be life on some strange planets, on small Neptunes and where liquid water exists because of the pressure and things like that. Really kind of weird stuff. I'm sure that weird stuff is out there. But there are a lot of Earth-like planets out there that are going to have atmospheres and are going to have oceans. And I tend to think we sometimes underestimate just how common those kinds of environments are. It's good to think about the extreme environments, I agree. But let's not forget that the common environments are going to be common.
More common. Indeed.